We're going to take a look at rocket propulsion in the context of conservation of momentum. What we're going to see is that the general, you know, expression for Newton's second law is not F equals ma. It's not force equals mass times acceleration. It's actually force equals the rate at which the momentum changes with respect to time. So what we're going to be able to do here is use that relationship and understand that when we apply Newton's second law, that we have to take into account that the mass depends on time as well as the velocity. So again, we look at rocket propulsion and we look at rockets in terms of a reverse collision almost. Basically, we're going to conserve momentum. We are going to conserve energy in these systems, not necessarily mechanical energy. But it's important to note that unlike an inelastic collision, a perfectly inelastic collision where two bodies come together and then stick afterward, here we have two different parts of the system, the rocket and the fuel, which is going to be used to create the propulsion, which start together and then end up being separate objects. So again, rocket propulsion is different from propulsion that we use, terrestrially, a road on putting a force on a car, tracks on a train, propelling a train forward as a train puts a force on the rails, and even a boat pushing on the water and an airplane pushing on the air. There's nothing to push off of. So really what we have to rely on when we're in space and there's nothing to push off of is we have to give up mass. We have to put momentum into this mass and essentially create a reverse collision. The mass from the thrust goes one way, the rocket is propelled in the opposite direction. Again, momentum is conserved. The kinetic energy of the rocket will increase as at the expense of usually chemical energy or electrical energy, which is stored within the rocket. Now, let's take a look at rocket propulsion and again apply Newton's second law. The most general form for Newton's second law says that force is equal to dp dt. And again, it basically tells us that the force that a body experiences is going to be proportional to, I should say, the net force is going to be proportional to that body's change in momentum with respect to time if it's in an inertial frame of reference. So here we can see this is actually a model rocket. This model rocket has some mass, we'll call that big M, and it's giving off dm, which is an infinitesimal amount of mass given off in an infinitesimal amount of time. So what is the force that it experiences? The force that it experiences will be equal to the infinitesimal amount of mass given off times the velocity that's given off divided by the infinitesimal amount of time that has gone by as that small amount of mass was given off. This will result in an increase in the velocity of the rocket, where it will increase by an infinitesimal amount of dv. So let's write this in an equation. I'm going to write Newton's second law, and we're going to take into account the rate at which the mass is given off and try to look at how that affects the overall change in velocity of the system. Okay, so here is Newton's second law. Now, once again, the problem that we run into is we can't use F equals ma here. And the reason for that is both mass and velocity are a function of time. So normally, if mass were just constant, as we've been using in most systems, we could put mass out in front and then just take the derivative of velocity with respect to time, and that would give my mass times acceleration. But in taking this derivative, I have to basically treat both of these functions as time dependent, and that's going to give me two terms. If you remember from calculus, when you have the product right here, you take the first member of the product times the derivative of the second element, and then you add that to the derivative of the first element times the second element. And that gives us this relationship right here. Now, it's important to note, I'm treating the rocket as though there's no gravitational force on it. All right. I'm just treating it like it's sitting out without any forces acting on it. It's sitting out in free space. And what I can do is I can take these two parts of the equation and I can separate them. And here, again, I look at what I have for as it's applied to the rocket. And I see here that the mass of the rocket times dv dt, okay, that's our F equals ma, the net force acting on the rocket, is going to be equal to and opposite to the exhaust velocity times the rate at which the mass changes, really how quickly it's using up its fuel, how quickly it's giving up this hot expanding gas in the opposite direction. So this provides a very useful differential equation, and I can eliminate dt on both sides. When I do so, I go from this equation right here to this equation right here. It's a differential equation which involves velocity and mass. We integrate the left-hand side in terms of the initial and final velocity. We know when I do this integral right here, I'm going to get delta V, okay, the change in velocity of the rocket. On the right side of the equation, I'm going to integrate mass, where mi is the initial mass of the rocket. That's typically higher, okay? On takeoff, the rocket is going to have 100% of its initial mass. And after it's used up all its fuel, it's generally down to about 10 to 20% of its mass. So mi is much larger than mf in this particular equation. And of course, the rate at which the mass changes is going to be negative here. So when I solve for this differential equation, it's very, very easy. Again, this becomes delta V, final minus initial, okay? So that's my left-hand side of the equation right here. On the right-hand side of the equation, whenever I take the integral of 1 over some function here, I get the natural log. Now notice my two boundaries, my two initial and final parts have actually switched. So I will actually have the natural log of the initial mass minus the natural log of the final mass, and then I can just write that as the natural log of mi over mf. And this is what's known as our rocket equation. This allows us to calculate how much the change in velocity will take place for a given exhaust velocity. This is very, very important. How quickly the exhaust is given off. Hopefully that is a constant value, so that makes this valid, because VE has to be a constant. But this natural log represents how much initial mass I have compared to how much mass I have at the end. Now, if I do include gravity, it becomes much more difficult, because the gravitational force will change as a function of position. And as we can see at takeoff, we can come up with a general delta V, subtracting off the effect that gravity is going to have. However, what we typically want to do is take this term right here, which really depends on the the kinetic energy, and this term right here, which is sort of an effective delta V. It's the delta V that we lose due to the gravitational force, or due to the fact that we're turning energy into potential energy. And generally, I'll come up with some delta V that just represents the delta V I need to get to a particular orbit. Okay, think about when a rocket goes into orbit, it has both kinetic and potential energy. And without going into this, generally, the absolute value of the potential energy is twice that of the kinetic energy if you're in a circular orbit. But basically, I can say there's going to be some delta V for some orbit that I want to achieve, and sort of go back to this equation right here and say, well, I want to get to a low Earth orbit. I want to get to a geosynchronous orbit. I want to get to the moon. I want to get to Mars, wherever. there's going to be a delta V cost there. And that's strange because we think of V as velocity, but in terms of orbital mechanics, this delta V represents, a particular orbit because that orbit has kinetic energy and potential energy that I need to, get to. I have a certain amount of energy when I'm on the surface of the Earth. I have a certain amount of energy when I'm in orbit. Okay. And again, this equation is going to help me determine that. Now, this basic equation for rocket propulsion, again, this delta V being a more abstract idea than just change in velocity. When we look at most rockets, MI divided by MF is usually between 8 and 10. What that means is, again, the rocket is going to have about 80 to 90% of its mass in fuel. So when I calculate this, I can see that I can get more delta V either by, burning more fuel, okay, or by producing a higher velocity of thrust. And that's why rockets are so energetic, because of this rocket equation. If I was just, and we used to do this for middle school students when we would have these different workshops with them. We'd make them build a rocket made out of a soda bottle. They pressurize and then force water out. Well, the water's coming out at such a low velocity that these rockets are very inefficient, but they're nice to just sort of watch as a demonstration tool. But for a real rocket, this exhaust velocity usually has to be in the thousands of meters per second before we can even hope to achieve an orbital velocity. So again, that's going to be very, very important to think about. Now, again, when we look at jet engines, we can use them, near the surface of the Earth and obtain very high effective exhaust velocities because of all the bypass air. Even though the air is typically going out of them at about 300 meters per second, because there's so much bypass air, it effectively acts like the thrust was coming out at almost 30,000, almost 10 times that. So turbofan engines in atmospheric travel are very, very efficient in order to propel ourselves. But, two things are limited here. One, you can only achieve a certain velocity before the efficiency drops significantly. And two, they're only good in the atmosphere. Okay. So when we are talking about rockets, there are different types of rockets that produce different types of effective velocities. Okay, exhaust velocities. So what you'll generally see are solid rockets are used to boost the rocket in the initial startup phase of the launch. These are not very effective once we get past the initial velocity, but they can produce a tremendous amount of thrust and take up the most of the workload on the first phase of launch. Bipropellant rockets, liquid methane, liquid oxygen, liquid hydrogen, liquid oxygen, liquid kerosene, liquid oxygen. These bipropellant rockets can get a much higher exhaust velocity, so that as we go from the boost stage to further up in the atmosphere, we need that higher efficiency in order to achieve orbit. Now, we will talk about some of these other types of propulsion later on, and we will see that by accelerating ions instead of using chemical energy to propel the exhaust can actually produce much greater efficiencies, larger delta Vs for the same amount of fuel that's burned. But at this point, we can only use chemical rockets to effectively get us out of the atmosphere. Ion engines do not work in the atmosphere. Basically, what happens is, as we shoot ions into the air, they're quickly neutralized, and effectively the engine doesn't produce thrust to any meaningful extent. Okay, so let's get back to this idea of delta V. Again, delta V in the past, we typically think of delta V as our change in velocity. Here, it's going to be really what is our cost to get to a particular orbit? And the cost to get to orbit is significant. We have to get an effective delta V between 9 kilometers per second and 10 kilometers per second, even before we can get to low Earth orbit. And that's what LEO stands for, low Earth orbit. If we want to go to geosynchronous orbit, we need an additional 2 kilometers per second on top of that. And then if we want to leave the Earth's orbit, basically its gravitational well, we need between 1.3 kilometers per second if we're already in geostationary orbit, and 3.2 if we're in low Earth orbit. And finally, to get to the moon, 2.8 from geostationary orbit, and 5.9 kilometers per second to get from low Earth orbit. So there is a cost to go. First of all rockets will start out by achieving low Earth orbit, even if it's for a very short amount of time. We stage rockets to effectively increase their efficiency. Okay. We did talk about this earlier in a previous chapter that rockets which are optimized for the surface of the Earth have a different shaped thruster than those that are optimized for space. Those that are optimized for space have huge thrusters on them, big parabolic cones compared to the ones that are used on the surface of the Earth. So by staging them, we increase the efficiency. We also stage the boosters. So once we're in low Earth orbit, we can then decide where we're going to go. Are we going to go to geostationary orbit? If it's a weather satellite, if it's a communication satellite, do we want to send it out into space to another planet? That's where you go to what's called C3, which is the essentially point at which you can get away from Earth's gravity. Are we going to the moon? Okay, so if we do a little calculation right here, let's say we want to leave the surface of the Earth and reach low Earth orbit. If it's a single stage rocket, 90% of the rocket's mass has to be fuel. Okay, and to achieve low Earth orbit, we would have used up 90% of the rocket's mass. Obviously, about 10% is going to be your payload, and the rest of the rocket itself, including rocket motors. And you can clearly see that a single stage rocket is a really bad way to get to orbit. Now, once that rocket's in orbit, 95% of its mass, okay, would have to be fuel to get to the escape orbit. So this problem is that you have 10% of the rocket's mass left. You'd have to use 50% of that. And again, this is the reason why we do staging, because we can get rid of the large tanks where we initially burn through a lot of the fuel early on and then use smaller tanks and smaller rocket motors. Now, here's a really good illustration, albeit it's a little bit complicated, of what it takes to get to different orbits. Again, 9.3 to 10 kilometers per second just to get to low Earth orbit. And this depends on where you're taking off from the Earth. If you're taking off closer to the poles, it's going to be more. If you're taking off closer to the equator, it's going to be less. But that's what it takes to reach orbit. The fact that the Earth is rotating, the closer you are to the equator, the more of a kick you're going to get to help get you to orbit. But again, you can see to get to geostationary orbit, how much it takes to get from low Earth orbit to Lagrange point 1 and 2, how much energy that takes to get to. I believe the Webb Space Telescope is in Lagrange point 2. And then low lunar orbit, how much energy it takes to get to there. and how much energy it takes to actually land on the moon. So we express this cost in terms of delta V, even though it doesn't really represent how much the velocity changes. It's related to it because there is some kinetic energy that is obtained when the rocket engine is in use, but a lot of it is potential energy that we're overcoming. This is a really neat map. This is called the subway map of the solar system, and this was done by I'm not going to do a great job of pronouncing their name, but they showed here what the costs are, almost like if you were in a subway system, what it would take to get from one place to the other. And you can see to go from Earth to low Earth orbit, it's 9,400 meters per second. That's a minimal cost. If I wanted to go to the moon, there's an intercept orbit that I need to go to, then a low moon orbit, and then landing on the moon. Okay. Of course, I'd have to reverse this whole process because going to the moon, as I go from the intercept orbit to the low Earth orbit, I'm actually giving up energy. So I'd have to gain that energy back here. And to leave Earth's influence, this C3 is really the junction to all the other planets in the solar system. Mercury actually takes more energy. You have to get rid of more energy to go to Mercury than energy that it takes to get to Mars. And that seems sort of counterintuitive, but the fact that Mercury is sitting so deep in the sun's gravitational well means that to get there, you have to give up energy. And of course, here is Mars, a very common place that we've sent space probes. Hope to send people there someday. But in addition to get, about 10,000 meters per second, or 10 kilometers per second to get to low Earth orbit, another 3 to get to the Earth intercept orbit, another 1 kilometer per second to intercept Mars's orbit, and then another, probably almost 2,000 to get to the surface of Mars. It's important to state right here that once we get into low Earth orbit, any additional delta V that we have results in an exponentially larger amount of mass. So, just because this seems like the largest part that we pay, as we put more delta V into the system, the overall cost in terms of fuel from initial to final is going to result in an exponential growth in the amount of fuel that I need. Now, when I want to change my orbit, all these delta V's were basically taking into account that I'm doing the most efficient type of transfer. This is what's known as a Holman transfer. If I want to get to a particular orbit faster, I would have to use less efficient means. So let's say that I'm in low Earth orbit and I want to boost to geostationary orbit. Okay. I would do a burn, in low Earth orbit. That would create an elliptical orbit. And then once I reached my desired radius, then I would burn again to circularize the orbit, and that would result in a delta V twice. Now, this works for everything. It works for an orbit around the Earth, going to a higher orbit, maybe in a moon intercept orbit. It works for leaving Earth's orbit. Okay, let's say that now this is Earth and this is the sun, and we want to get to Mars. This transfer is actually done twice. And the problem with this is when we get to ion engines, which have a very low thrust, they actually lose some efficiency because the low thrust means that, unlike a chemical rocket where we can produce a large amount of thrust all at once, we're not producing this delta V, at the optimized point in time. So, with ion engines, we can actually cheat a little bit and give ourselves a little boost and maximize the efficiency. In any case, a burn to increase the radius, a burn to circularize the orbit, and that's essentially how we transfer from one point to another. Now, using this type of transfer to get to Mars, we see that this creates quite a problem for us. Let's say that we have a spacecraft and we want it to depart from the Earth, and we do this transfer to Mars. In this case, it would take us a few months to get to Mars, okay? Not so bad, right? But let's say that once we're on Mars, we want to return to Earth. We can't immediately do that. We have to actually wait for Earth to catch up with us, to lap us once in the orbit, and then we can depart from Mars. But as we can see, this means that I am going to take quite a long time, almost 3 years, for a round trip journey to Mars. Now, for a space probe, that's no problem. When we drop the Mars rovers off, we are not expecting them ever to return. For human missions, this would be quite a commitment for somebody to travel to Mars, even if they intend to return. And that's about 919 days. And again, we look at the delta V, that would be a delta V of 17 kilometers per second, as opposed to getting to the ISS, which is only 10 kilometers per second. Again, it's not that we need 70% more fuel. That's not how this works. This is an exponential growth. So we need something much, much larger than the rockets that take us to the ISS. Okay, let's look at something else, which is somewhat related. It's called specific impulse, and it's a way to analyze the efficiency of the rocket engine. Instead of looking at these orbits in terms of delta V, this looks at how much thrust we can get, okay, how much force we can get for a particular amount of fuel that's burned. So when we look at specific impulse, which is written as J, remember J was our impulse, we use the subscript SP. It's asking, well, how much force do I get by burning so many kilograms of fuel every second? That's our specific impulse. And what we notice here is that the faster we go, the more the specific impulse drops off, okay? In fact, sometimes we'll actually normalize the specific impulse to gravity. So instead of having newtons per kilograms per seconds or newton seconds per kilogram, by putting meters per second squared, we change this to seconds for a specific impulse when it's normalized to the acceleration of gravity. And again, here's our problem. Power equals force times velocity. So the force that we get is going to be equal to the power divided by the velocity. Power, of course, is related to the energy per unit time that's used. And this is related to the work that the engines are doing. So we can see that planes have a very high specific impulse, mainly because they're going so slow, meaning that we can get a lot of force for the amount of fuel that we burn. As we go faster, however, the force generated becomes less for the amount of fuel used. And we see this with supersonic transports such as the Concorde, okay? Or on the SR-71, it gets even worse here. That is the Blackbird, the fastest plane, where our specific impulse drops even more. For the space shuttle engines and the engines that are used on Artemis, we can see that once we start traveling up to Mach 10, this specific impulse becomes much, much less. So you'll see different engines rated not only in terms of their exhaust velocity, but also what is their specific impulse. That's a real nice way. When we do apples to apples, going at the same speed, looking at the specific impulse really tells us our efficiency, because it tells us how much fuel we're burning to obtain a particular amount of thrust. Okay, so let's take a look at different rockets, and everything down in green right here is cheating. It's pushing off the air. So they have an effective exhaust velocity that's much higher and a specific impulse, which is much higher than what we have for rockets. But in looking at rockets, um, your bipropellant, rocket motors, generally have um, effective exhaust velocities between 3,000 and 4,000 meters per second. And that gives us a specific impulse between 300 and 450 seconds for normalized specific impulse. And again, this is what we're left with. If we could use, uh, jets to accelerate us in the initial boost phase, um, we would obtain much more efficient velocities or much more efficient boosts. But again, our atmosphere is really very thin compared to how high these jets can travel. And really, something in orbit's going Mach 20, Mach 30, these jets are only good below Mach 1 for most of them. And I think Mach 3.5 at best. So looking at rocket motors, again, the solid rocket is used for the initial boost phase because when we're going very slow, specific impulse isn't as critical. Solid rocket motors tend to be very inexpensive. You can just discard them. But in terms of efficiency, they provide very low amounts of energy for the amount of fuel that we burn. Great for boost phase, the initial boost phase, they're the workhorse. But as the rocket gets going faster, we rely on bipropellant liquid rockets. And this 4,400 meters per second for an exhaust velocity really represents the best that we can hope for by chemical means. Now, again, going to this idea of using other forms of propelling the rocket. Now, remember, when I used the example of the water rocket, the rocket was being pushed one way as water was being forced out the other end. Okay? It was a great demonstration tool, but with regard to the overall efficiency of a rocket, we need a fairly vigorous and violent chemical reaction to produce a high exhaust velocity. And that's why we use these very reactive chemicals, which can result, if things go wrong, in a massive explosion. However, once we're in space, we can use other means. We're not just restricted to using essentially a chemical reaction that superheats a gas, the gas being at thousands of degrees, then tries to expand. We expand it through these parabolic cones that provide us the thrust. What if we take an electric field and we accelerate ions and we use electrical energy instead of chemical energy? Here we can see that obviously using ions seems like a much better idea. At these velocities of tens of thousands of meters per second, or even hundreds of thousands of meters per second, we get much better specific impulses. We get much more energy than we get from the chemical rockets. But again, remember, we're stuck with having to go through the atmosphere, okay? We're stuck with the fact that we have to get out of the Earth's gravitational well so that chemical rockets provide a large thrust, and they also can operate in the atmospheres where ion engines cannot. So again, turbofan engines, high specific impulse, but they're able to do that because most of the air actually bypasses the jet engine. So they're pushing on a lot of air. That's the key thing here. We're pushing on a lot of air, creating a large amount of thrust. Solid rockets on the boosters, incredible amounts of thrust, 13.8 million newtons of thrust on takeoff for the space shuttles boosters when they used them. For Artemis, I think it's a little bit more than that. Maybe it's 15 million newtons. But again, we use these for just the initial phase when the rocket actually has a fairly small velocity. Once we start going into the higher velocities, the thrust will drop off very dramatically. Now, again, for the shuttle, the solid rocket boosters provide about 83% of the initial thrust at takeoff. For Artemis, it's probably pretty close to the same, but the low specific impulse makes them ineffective once we get the rocket going. This is the Delta IV Heavy, was recently retired. It's going to be replaced probably by some variant of the Vulcan, but it's a bipropellant rocket, meaning that it uses an oxidizer and a fuel, liquid oxygen and liquid hydrogen in this case, and very, very efficient in terms of the fact that it used hydrogen, which is a difficult fuel, but has a very high specific impulse. These RS-68 engines have a very large specific impulse, about 412 seconds. And they're very effective in producing an efficient means of getting to orbit. Now, the first bipropellant rockets basically used grain alcohol, ethanol, and liquid oxygen in the form of the V2 rockets. However, more efficient systems were developed where purified kerosene and liquid oxygen were used. These were used on the Saturn V first stage and are still used today on the Falcon 9 and heavy rockets. The shuttle's main engines used liquid hydrogen and liquid oxygen, as does Artemis. Newer engines are switching to liquid methane and liquid oxygen because there's sort of a compromise. The kerosene liquid oxygen engines were easier to use for a number of different reasons. Again, hydrogen likes to leak out of everything. However, they had a lower exhaust velocity than the Hydrolux motors. However, methane, being a smaller molecule than kerosene, being more rich in hydrogen and less rich in carbon, produces a more energetic reaction, produces a higher exhaust velocity than kerosene and liquid oxygen. However, it doesn't have as high of a specific impulse as Hydrolux, but it gets away from some of the problems that we have with hydrogen being just this little sneaky molecule that likes to make it out of everything. Now, ion engines, great for some things, as we'll see, very limited for other things. Ion engines, again, use an electric potential. All we need is a higher potential and a lower potential. We put a little ion between them, and if we put a hole in one of the plates, the ions will be attracted to that negative cathode and accelerated, and we can just send the ions off into space. Here's the problem. Once again, they can't be used in the atmosphere. If I send an ion through the air, it will quickly be neutralized, and therefore essentially won't accelerate across the plates. The other problem you have is today's ion engines don't produce very much thrust. Most of these ion engines produce less than a Newton of force. That's not going to get your rocket off the launch pad. Additionally, they need huge amounts of electrical power. As we'll see, some of these will actually use almost a megawatt of power, and that's beyond what solar powers can produce. But once a rocket's in space, even though they produce a very, very small amount of force, unlike chemical rockets, which you only burn for a few minutes, you can keep this on for months. You can keep this on for years and just get a larger and larger orbit and get to our final destination much more efficiently. And again, going back to this chart right here, notice how much greater the specific impulse is for an ion engine compared to, say, a solid rocket or bipropellant rocket. In terms of, the most advanced ion engine that's being developed, you can obtain almost 100 times, the specific impulse, more like around 40 times the specific impulse of a bipropellant rocket. And that produces massive amounts of improvement in terms of the overall efficiency of the system. So the general thought is this: we boost these rockets into some orbit, and then we use the ion engines to get to a higher orbit, or for the case of low Earth orbits, for instance, the Starlink satellites have these little ion engines on them. We're thinking about putting ion engines on the Gateway space station to the moon when that is launched. This idea that we can maintain an orbit without using very, very much thrust. The ISS actually still sits in the atmosphere a little bit, so atmospheric drag is constantly trying to bring it back down to Earth. So every time we bring cargo to the ISS, I shouldn't say every time, once in a while we have to boost its orbit up a little bit to maintain that. This is the SPT-140 ion engine. It's a Hall thruster. This actually is the new star. This was used on the first satellite to ever use ion engines, and that was Deep Space One, which visited asteroids, I think back in the 1990s. But today's ion engines are even more advanced. This Hall thruster basically has, pretty good power demands between 900 watts and 4.5 kilowatts. But that's a power that can be handled by most, solar panel arrays that we have on space probes. This is being used on the Psyche mission to the metal asteroid Psyche, which is going to investigate that asteroid, because some people think that these metal asteroids would be great for mining materials. So this Hall thruster is very much optimized for this type of mission: low mass, modest energy consumption, high specific impulse, 1,800 seconds, not much thrust, between a quarter and a fifth of a Newton. But again, it's designed to be on for months. And the thruster mass is only 8.5 kilograms. So, effectively in the system, you would have to include not only the mass of the thruster itself, but the mass of the solar arrays when you take a look at the overall system. But think about it this way: chemical rockets, where's the energy coming from? It's coming from the chemical reaction. Here we're getting away from that. We're getting our energy from the sun. We're getting the energy from the solar panels, okay? We still have to use up fuel. We use xenon in this case. We accelerate xenon ions to very high velocity to produce our momentum. But the nice thing about this is that we don't have to rely on the chemical energy of the xenon. The xenon is really inert in this type of system. We simply take the electricity, accelerate this, and you can see the blue glow from the xenon ions coming off of this. The most advanced ion engines have much higher energy requirements, so we may not be able to use just solar panels to power them. This is a dual stage 4-grid ion engine, and it'd be approximately 10 times better, 10 times more efficient than even our present ion engines. But the problem is their energy demands are huge. This type of engine is going to be heavier, so it needs to be more efficient to make up for that difference in mass. But the power requirements for this are about I think I overstated this, about a quarter of a megawatt. This should be greater than 250 kilowatts. So I apologize for that. But that would require 250 megawatts would require a huge nuclear reactor. That would require a sizable nuclear reactor to power. Again, you would get much larger thrusts, still probably in the sub Newton range. To get really large thrusts, another type of ion engine has been in development called the Vasimir. And this is less efficient than some of the other ion engines, but if you need a huge amount of thrust, you would need a system that obviously expels ions at a much greater mass rate than the smaller Hall thruster. So again, what can ion engines do for us that chemical engines can't? If we look at the amount of fuel that we use compared to the total mass of the rocket initially, we get this equation right here. Now, again, ion engines aren't going to help us to get to low Earth orbit. But let's say we have our chemical rocket platform. It gets our payload to low Earth orbit. How we get someplace is going to depend on the exhaust velocity of the system that we use to now boost it higher. So again, delta V from going from low Earth orbit to geosynchronous orbit, it's about 2 kilometers per second. The delta V from going from low Earth orbit to Earth transfer orbit is about 3.2 kilometers per second. So if we used a booster, once we're in low Earth orbit, to get to geosynchronous orbit, we would use half of the fuel, and this is the fuel that we've already put up into orbit. Okay, for geosynchronous, and almost 3/4 for Earth escape at C2. Biopropellant rockets, we see we do much better. But look how much better ion thrusters are. 72% of the rocket's mass would have to be, the solid rocket itself. Over half of it would be bipropellant rocket, where the ion thrusters would only take up about 10% of the total mass. And if we could go to this dual stage thruster, we could drop that down to, a few percent. So again, when we look at these ion engines, they really do greatly improve, what we need to get from point A to point B. To get to Mars, we need an even larger delta V. We need, 15,000 meters per second. However, only chemical rockets can reach low Earth orbit. So the required delta V to reach low Earth orbit would be taken up by chemical rockets. But then to get to Mars, okay, we would need 88% of the mass of whatever we put in low Earth orbit to then get us to near where we need to go. So basically, the remaining mass of the spacecraft will be dictated by the type of propulsion that we use to go from low Earth orbit to Mars. For instance, the Orion spacecraft, which is the current rocket designed to go to the moon and go to Mars, its mass is 10,000 kilograms. Modifications to Mars would probably up the total mass to about 30,000 kilograms, which means the rest of the mass beyond 30,000 kilograms would have to be fuel. Now, to calculate the additional mass, that we need to go to Mars from low Earth orbit, we assume a delta V additionally about 11,000 meters per second for the out and back journey. And again, if we're just using a solid rocket, the mass of what we'd have to put in orbit would be, 2.4 million kilograms. Even the Starship rocket, which is being developed, doesn't even come close to that in terms of what it can put into payload. Biopropellant rocket, 370,000 kilograms. But again, if we use ion thrusters to get these human, carrying rockets to Mars, we begin to approach more realistic values for our Mars rocket. Just looking at the different platforms that we have right now, the most powerful platform that we have to put rockets in the orbit is the reusable Falcon Heavy. Can place about 63, about 64,000 kilograms in low Earth orbit. That's not going to work with our Mars rocket at all. But we could conceivably place a human rocket in orbit with this platform. SLS can probably place between 150,000 to 290,000 kilograms into low Earth orbit, depending on its configuration. But again, that doesn't get us to where we need to get to make it to Mars with just bipropellant rockets. So the way we envision our Mars rocket is probably using ion engines to get the Orion spacecraft to Mars. Obviously, because Mars does have an atmosphere, even though it's very, very small, and because its gravitational field is too great for ion engines, we'd have to use chemical rockets there again. But just doing the numbers, an ion engine makes more sense to get human beings to Mars than the current bipropellant rockets that we have. Here's the other problem that we run into with the ion engines. I'm painting the ion engines like, again, they're going to cure all our problems. We can't use the ion engines with the amount of thrust that they produce right now and solar panels to get us to Mars using Hohmann transfer, which those previous numbers are really utilizing. We would have to use a nuclear reactor to basically power very large ion engines. And we don't have a nuclear reactor developed. We're getting there to power this system yet. And we don't have the size of ion engines that we need either. So again, ion engines seem to be the solution to this problem. But in terms of the point at which we've advanced, we don't have that system up and running yet. Starship, as I said, probably can put over 100,000 kilograms into orbit, but even Musk has said that to get his bipropellant rocket from low Earth orbit to Mars, he's probably going to have to refuel it. Okay, which means several Starship launches just to put one Starship to Mars. And the idea that they have at SpaceX is that they launch several tanker Starships to fuel the Mars-bound ship that way. So in terms of the future of rockets, probably look very different from the types of missions that we've had today. We still have these high fuel ratios of chemical rockets that make them very inefficient, very dangerous, and very expensive. Some of that's been improved with reusable rockets, such as the Falcon 9. But future rockets may actually use a different way of making them reusable. And they may also take the advantage of pushing off the atmosphere, where hypersonic ram and scramjets could help boost payloads into orbit. Obviously, once we're in orbit, ion engines could take over and then get the payloads to wherever they need to go. Now, we've experimented with different type of hypersonic aircraft, but again, that's not a technology that's even close to being developed. For transorbital flight, probably we'll see eventually getting away from chemical rockets. Once we have payloads in orbit, we're probably going to have to rely on some type of ion engine. And this ion engine will probably not just be powered by solar panels. it'll probably be powered by denser sources of energy, such as nuclear energy. So again, just to summarize this section, we have an entire chapter on rocket propulsion. We could have an entire course on rocket propulsion. You can do an entire major on the engineering of this, but we have a limited time. So just to summarize, the specific impulse, again, which is often normalized to gravity, is a good means of telling us how efficient a rocket is. So if you hear about the specific impulse of a rocket motor, that's telling you a lot about how effective that is, how efficient it is. Delta V looks at the minimum fuel costs based on particular exhaust velocity. The faster you can make the exhaust, the more delta V you get for an equivalent amount of fuel that's used. And really, our biggest problem is leaving the Earth's surface. Okay, it has the largest delta V cost, making it very difficult and expensive to put objects in orbit. Once we're in low Earth orbit, we can use higher exhaust velocities from ion engines in order to achieve greater efficiencies and get to where we need to go.